Hello everyone and welcome to Handmade Hero Show Recode Complete Game live on stream. We have some debugging to do today. In fact, because if I remember correctly, last weekend at the end of Sunday's stream, we finished up at a point where we had done the plumbing necessary to take light probes and push them out into a voxel. And then we could compute on that voxel if we wanted to. It's in CPU memory. It's on the CPU side. And then at the end of every lighting computation, we push the voxel down to the graphics card and sample from it. And where we were at, we finished that sort of, it's running. But it doesn't quite work the way we would expect it to at the end of last stream because we pushed some sample information into the light probes and wanted to see if it would come out the other end, and it didn't quite. And so what we want to do today is start debugging that process. So what we'd like to do, best case scenario, end of the day, what we'd like to get to is a clear sort of structured art situation where at the start of the lighting computation, we initialize light probes with some specific data. So we verify that we can put specific data into our light probes. We then don't really run a lighting computation because, again, we want to leave a specific set of stuff in the light probes. So we skip the actual lighting computation. We then output the light probes into the voxel, and we verify that the voxel shows that same structured light that we put in at the head end. And so that just tells us that we've debugged like any of the sort of pieces that could have failed there. And so that's what I really want to get to at the end of the day today. And that sets us up for the next step, which is actually simulating the lighting, which is kind of the final stage in producing a new working model of lighting that works on the light probes. And then from there, we're kind of off into optimization territory. Like seeing if we can make sure everything runs fast enough. First, by limiting our region. Right now, I think we consider way too many light probes. I think we're just considering all the light probes. Oh, excuse me, it's way too early for me to be up. And then we go from there, right? So let's start off just by taking a look at what I was saying was broken about it. This is in debug mode, so it's a little bit slow, but even in debug mode, it's fast enough to run. And what you can kind of see is actually there is something going on, right? You can sort of see there is some lighting showing up. It appears to be very high, like above the hero or something, and we're just kind of popping up into the bottom of that lighting, perhaps. Again, it's pretty hard to see. Most of the world is unlit, right? You can kind of see that really we're not getting much in the way of lighting there anyway. But there is something happening. So it's a little bit confusing because, if we had just a straight up, like, nothing's getting transmitted kind of a bug, then we wouldn't see that lighting popping up. At the same time, we're getting almost no lighting popping up. So it is a little bit weird. And it's kind of difficult to guess what's going on. I'm curious if I hop over to an area where there's a stack of things here and I hop downstairs, what do we see? And one of the things that I notice is I'm still not seeing, like, there isn't light up on the top level here. So if I had to guess, and I don't really know, but if I had to guess, what it looks like is happening to me is that our scale is wrong. So it looks like, because I can see some lighting when I hop up into it, I'm thinking that our scale is wrong and the size of the light is just very small for some reason, right? So maybe when we put it into the voxel or when we take it out of the voxel, or who knows, what we're getting is that lighting information is just really, really tiny. So, because remember what we stuffed in, like test data, the assumption there, oops, I shouldn't have closed that. The assumption there was that we stuffed in the test data correctly at the same size as like a big sphere that we could see, of a big sphere of lighting. And my first question is just, did we actually do that? So here is the light probe index, right? And we're looping over it. You can see us doing our add probe to spatial index thing here where we add light probes into the spatial index somewhere. And then we come through here and we tried to run the same code. This is exactly the same code. We tried to run the same code we were running before where we said, look, let's try to put the light in here that we were using for putting it into the voxel directly. Let's use it to put in the light probes. Now, one of the things that might be busted about that is we've got this light RC here. That's a value that multiplies the light distance itself. This could be very wrong as well because, again, this is in world space. And so, you know, this was previously, I guess, in UV space, actually. And so it may just be a question of the, you know, it might be the only bug we have is really we forgot to update this parameter. And so just looking at it offhand, that is obviously incorrect because this is an equation that does the fall off. 1.0 is no fall off. So as this, you know, 1.0 would be no fall off, 0 would be complete fall off, right? And so this value has to range from 0 to 1 over however large the light source needs to be. If this RC value here is 3, that means that our distance fall off is 3x times the actual world space distance. That means it would fall off at 1/3 of a meter. That's a very tiny light source. And hey, that happens to be what we're seeing. So what we probably want to do here is actually change this into something that is the correct meters fall off. So for example, we could say 1 over however many meters we want here. And the light, you know, let's say we want a 10 meter fall off of our light source. I don't know what we actually want it to be. But let's say we did that. Would we now get a sphere that we could actually see properly? You know what I mean? That would be my first question. And so running Handmade Hero now, here is the actual game running. And there we have, well, so, you know, now we actually do get some visible lighting there. But one of the things that's really interesting about that is it's apparently not really quite a sphere the way I would expect. Wow, that's a really interesting lighting artifact as well. So it is kind of spherical lighting. You can see it falling off as the sphere goes. What's really interesting is it seems like, and correct me if I'm wrong, but it seems like the answer that the light probe system is getting at the point where the voxel falls off to 0. So where there are no light probes, right? Where there's no light probe in a particular voxel entry, it actually goes to full bright there. You see what I'm saying? Somehow, it's really weird, but it creates an incredibly interesting effect. I'm not sure it's a super usable effect because it's going to have a lot of artifacts the way that it works. So I don't necessarily think we can harness that effect for anything particularly cool. But boy, that was interesting. It almost looks like a Pac-Man level inside the voxels where they fall off. That's a pretty interesting thing. So it does look a little bit there like, you know, it does look a little bit to me like we're getting the correct size fall off now a little bit. It seems like the light intensity is a little wrong, though, too. It's not that bright at the center, which is a little bit weird. And I'm not sure, I don't quite remember what we were doing. I don't remember if we changed the brightness there. I don't think we did. I think the light intensity is the same light intensity it was, right? You know, I guess I just can't remember. And so I don't know if we're seeing something weird happening there with that light intensity. I guess not, because if you think about it, the light intensity is at 10. And so this is a quarter of light intensity. That would give us maximum light intensity. And so if we wanted it to be more bright in the center, that is what I would expect. So I'm not sure what we did there. I don't quite remember, I'm sorry, if we changed that or not. I'm very tired today. I'm super sleepy. So looking at that, it does look a little bit more correct, like we're getting full lighting there in the center region, I guess. So that's not too concerning. and it does look spherical. So I think we're getting closer. But it seems like we still have some bugs where I'm not sure what's happening in the voxels at the location where there is nothing in the voxel. And I think we need to look at basically how we're handling our 0 or our null, like our not present value. I think that's probably getting handled incorrectly. At least that's my assumption, right? And probably what we're doing there is, providing some lighting that's getting thought about the wrong way. I think I kind of have a mental model even of why that's probably wrong. So we'll see as we go. All right, so if we take a look at what's going on with these voxels now, and you take a look here at the add probe to spatial index, what we're doing is every voxel we fill with light probe information by putting the closest light probe into the voxel at that location. When we fill the light probe with information, we're filling it with information about the light probe, which is at a particular position. Right? And so the light probe itself isn't centered in the voxel, and that creates a little bit of a problem too, right? And so I feel like we can maybe start to address some of our problems here also with the way we're sampling things by thinking about how this information is getting pushed down. If I go look here at how our voxel was being set up here, you can see that computing light directly in the voxel sort of has some benefits, because when you actually then go to sample it, you've gotten an exact answer at the center of your voxel. Whereas now what we're doing when we go through these voxels, right, is we're taking out what is actually in the voxel at that location. And I think our 0 voxel, in theory, when we go through our light probes here, right, one of the things you'll notice is we actually do have a 0 probe. And that's kind of wrong, right? Like, we don't want our probe to have a position. Just looking at where our light probes are, our 0 probe we don't really want to be anywhere, I don't think. And so we kind of want the 0 probe not to be in the spatial index and not to have any light in it at all, right? I think so that kind of has to look like that. And then when we get the 0 probe out, in theory, the 0 probe should be just skipped. So when it comes out here, we just need to do this basically, right? And say, look, if there's nothing there in that particular voxel, then we don't put light into that voxel at all, right? It's just blank. Assuming that we do something like that. That's at least a little more correct now on what should be occurring around the voxel. Okay, that was surprising. Probably because I needed to do a not equal to 0. Oh wait, no. Boy, I am so smart. That was correct. So the probe index comes out. If it's correct, we use it. This was the problem right here. We need to move forward every time. Otherwise, we'll always be stuck on the first one, right? Furthermore, in here, yeah, just looking at this, I think now that should be iterating over all of the parts of the voxel. I'm way too sleepy today. I had to get up early. My brain is not ready to do programming this morning. So you can see now we're not getting that weird sort of fall off artifact. And so we're able to do the lighting a little bit more appropriately now, and it is sort of doing the spherical fall off. What you can see, however, is now, because it's based on where the lighting probes are, each light probe right now has a particular value. And because it's based on where the lighting probes are, you can really see the problem with the way we're doing the sampling. And so I think, like, right off the bat, what we're going to see here, and, we can certainly play with it from here. We may have some bugs in there and whatnot, but what you can see, I think, right off the bat is just, it doesn't really work to do the lighting sampling the way that we're doing it there, for, like, a number of reasons, right? Like, because we're just putting light answers directly into the voxels and trilinearly them, we lose the light probe location information that we kind of needed, right? because we compute, unless we wanted to change and we actually just compute light at the voxels themselves, then the light lookup really needs to work here, and it doesn't work, right? And so just looking at how this is working, I really don't think we're going to get anywhere with this particular model. Just looking at how bad that trilinear sampling looks, and yeah, there could be some bugs in there. Maybe it's looking worse than it should look, but I just don't think we're going to be able to get all the way there with trilinear. I don't buy it. And so I do think the first thing we may have to do, because it looks like we are sort of pushing down the light probes properly now. I think the first thing we may have to do is start actually doing our own light probe blends in the sampler itself, right? In the fragment shader. So as painful as it may be, I do think like we may have to do something where we are actually pulling some kind of lookup information out of the voxel, assuming we still use one, assuming we still use a voxel. Because we could use other spatial partitions, right? There's nothing that says that our fragment shader can't itself do the lookup. But basically, something that tells us how we're going to blend these things together, I think might have to happen, right? I think pulling directly out of the voxel the lighting information is not going to work. And so what we may have to do is something more like, okay, we actually pull out the light probe positions, and then we do our light sampling on that information, and we use the actual position of the light probe too to figure out where the light is coming from relative to us, which is not the same thing, right? That's quite different than the way that it's working at the moment, where we just assume that it's coming from the center of the voxel, which in this case it may well not be, right? So I think that's probably what we want to do. I would like to do a quick check to see if where each of these things falls in the voxel itself. So one of the things that's a little bit hard to see right now is where does each light probe fall, in which lane of the voxels does each light probe fall. So if I were to go into the thing that outputs the light probes themselves, and in here we just said, look, I'm going to need inside the code that pushes the cubes down. Instead of doing this debug color, if I was to just set each light probe to just be pure white, so when I run it, all of those like color, the cubes that are colored sort of randomly, that are the light probe locations, if instead of that we just push down a full white, right? So you can see they're just white now. If I then go and change our voxel to be stuffed with something that shows like the checkerboard pattern, so like, for example, in here, if I were to change the light east, light west, that sort of thing, if I were to change, and so instead of doing any kind of light packing, like in here where we're actually taking the probe values here, right? If I was to change those up and said, let's actually give ourselves a checkerboard again, so something like this, right? And then I set everything to just be a neutral amount of light in the a neutral intensity, like so. Oops. So in this case, we just initialize everything to a neutral intensity for our inbound lights, like this. So we have west, east, south, north, up, and down here. So we initialize a neutral intensity, and then on our checkerboards, we turn, like every 2 squares on each, we turn on red, green, or blue. So we have red checkerboard along X, green checkerboard along Y, and blue checkerboard along Z. I just am interested to say, like, okay, so if we look back at the game, you know, and maybe, you know, the other thing that I might do there is let's restart without the bilinear on. So if we go over to the OpenGL renderer side of things, and we look at the linear call, so in here where we, that's our special textures. So in here we have our voxel. If we want to just have nearest here, assuming that we want to do something like that, and we go ahead and run the game without any filtering, my question is just, what will that show us in terms of who is, like, for each lighting probe, which ones are in which places, right? And so if you take a look at the way the lighting probes are aligned here, you can kind of see I mean, I guess one of the problems is since they're actually using the reflection equation here, I do wonder if maybe what we want to do is something a little bit more drastic there. So I think maybe I want to do something more like this. So let's suppose we have a light override value. This is the light color we're going to override everything with. And maybe what I want to do is make the checkerboard pattern just override all of the lights. So here, instead, what we're going to do is just, like, no matter what light direction you're looking, you're going to get the same light value, you know, everywhere. I guess I didn't need to close the game, but did. And now I just want to kind of see if we can pick out, like, individual light probes, and are they actually falling into different locations in the voxel or not, and so on, right? And so if I hop out to, like, a zoom level here, so here's, like, a particularly high zoom level, a particularly, like, far out zoom level. And we just look at, like, how are these things falling in the voxel. It does appear that, like, we generally get pretty good separation, right? So you can kind of see that there's plenty of voxel resolution for lookup through all of these, including the up-down, right? And so we do, I think, fill our voxels pretty reasonably. And I guess, you know, we have to make sure that each voxel is filled with something, I suppose. And so that's kind of a separate question. So I guess what we could do is say, look, if we turn off the sampling here, so I'm going to nuke the override. Right? And so, why do I keep closing it? Sorry, I keep closing the game for no reason. Excuse me. So if we go ahead and run the game, and I'm going to go ahead and hop out to that same location with the override off. I'm curious what will happen if we then test to see, like, I think part of the artifacts we're seeing here is when we are sampling from these lights, we're also perhaps seeing some places that don't have any samples at all, which is also probably happening. But if you look at the non-trilinear version, so if you just look at the raw, like, sampling that we're getting, you can see that it does still more or less look correct, right? So again, I think we're mostly there in terms of, like, sampling things in using the kind of sampling that we are doing here. But what you can see pretty obviously from that is we're just not getting, it just doesn't work to look up light probes that way. Blending as efficient as trilinear through the voxel may be in terms of the small number of lookups we actually have to do, it's just really not producing a particularly compelling result. And so what I think we may have to do is say, look, let's take each of the light values that we got, and we'll, you know, say that each probe, you know, we know, let's do some kind of indirect lookup so we can actually find out, you know, where each probe was, and let's account for the positioning of the probe when we sum the lighting there, you know, or something more like that. So that we can actually have some reasonable understanding of the incoming light. And furthermore, you know, one thing we may want to do is drop the resolution of the probe distribution as well. Because it may be that we're putting too many probes in, and that, you know, sampling the lighting that densely may not really work particularly well for indirect lighting, because it may be that that's just too dense of a sampling, and reconstructing from too dense of a sampling will just have too many artifacts, because you're just trying to fundamentally get more resolution out of the scheme than you can, because remember, the lighting that we're sampling here is getting smacked down very aggressively into just 6 directions of incoming light, which is not a particularly good representation of it, right? So it's pretty hard to say. I mean, and other things that we could point out here is we may also want to try changing the way that we're doing the light sampling, right? Like, with the light storage. You know, going to some kind of a different basis that's not cube directional might be another example of something we wanted to try. You know, this is why people use things like spherical harmonics and stuff to just have better ways of representing inbound light, you know. So that maybe that part of it is the cube sampling isn't going to work either. So we've got a lot of things to consider, but, you know, we're basically where we need to be. We just need to now start playing around and figuring out what's going to work. So let's take a look back at that Z-bias shader again, and just see like what exactly is happening here that we might you know, what do we want to do in terms of the shader here that would still have some chance of running reasonably per pixel, but that, you know, at the same time will let us do something better with the lighting. So you can see here what we're effectively doing is we're just relying on this sampling of the light information here. And you know, I again don't really know. There might be something we can do here, but there might not be. I'm not sure. One example is for if we added another voxel that just told us a position, you know, maybe that would be sufficient, so we don't have to look up into, so we don't have to do the indirected lookup, right? So one thing we could imagine here is, let's suppose we added one more voxel, because we know that seems to be fast enough, is having the voxel lookup. So, you know, suppose we took one of these here and said, all right, let's take a position. So we'll say like light P, and we'll actually ask, you know, can you give us a light position value out of this thing? And maybe we, you know, it's going to be a 3 wide. Maybe we can pick an encoding that lets us get some reasonable resolution there, right? And so, and you know what, another thing about it, we probably don't even need that really, so we probably can just sample it in a pretty basic way. But anyway, so imagine we get a sample here. We pull out a position of a light, and we could use that to just say, look, why don't you tell us where the light is relative to this voxel, right? So maybe what we do is we say, okay, we know where the voxel location is, right? This is like the center. Sorry, not center of the voxel. This is like the location of the position of the person inside the voxel space, right? And then maybe, you know, here we can say, well, where was this light probe in that voxel space, right? Like where in this voxel is the actual light probe similarly, right? Like maybe we get that information out of it or something like that, so that we have an idea of where it's coming from relative to where we, you know, actually looked up in the voxel. So doing something like that would allow us to reconstruct a world position. Unfortunately here we never really construct a world position of the actual voxel location itself. So we would kind of need to compute the voxel center P before we could apply a displacement to it. But again, we could sort of cross that bridge when we come to it. We could even pretend that we're sending down a full floating point, you know, 3 float texture here or something like that for the moment, and, you know, avoid the encoding problem, and then do the encoding problem off of the voxel as a separate step. But if we assume somehow we're going to get a light P out of this, right? Maybe I'll call it this. So we get a light P out of this somehow. Once we have the light probe position, then when we actually get the light data here, we have a average amount of light that we compute and a position that that light is coming from, right, as part of the fetch. And so if we did that, then in theory we could adjust how that light is falling on us based on our positional offset. Now, I'm trying to think, does that really help us? You know, it might not. It might require, in order to do this properly, we might have to do these fetches without the blending, right? So that we then compute the lighting on each of the probes separately and then blend the result of the lighting computation together. And I don't really know. Like, just thinking it through, it's hard for me to really tell what I think would really be happening there. And when we look at what the fall off of the lighting is going to be in terms of it falling on the surface here, you know, we kind of can add in the fall off based on how far we are from the probe potentially. But again, that's very difficult for us to really imagine because we don't, you know, the light itself contribution is falling off. So I mean, just looking at this, I'm just thinking like, what would I really do with that? And I don't know. So again, I think just looking at this, I can't really tell what I would do without turning off the sort of the interpolation on the voxel and actually just getting literal values out of it, right? And doing the blend myself. Yeah, I mean, I just unfortunately can't really think of anything else to do there. And again, you can see why I don't want to do it because the number of texture fetches just goes up so incredibly much. Each one of these is like an 8-way texture fetch, right? Yeah, I don't know. I'm trying to think in my head if there's anything that I'm like missing that would make this process smoother, but I just don't see it. Because again, like what we're trying to do fundamentally speaking is use the position of the pixel of the fragment, the world space position of the fragment that's being lit, to compute a lighting equation that actually properly responds to its position relative to the wherever the light was sampled. And the problem is that when we if we just do a trilinear filter on what we know these values are, it doesn't seem to really, I don't think that's going to interpolate as well as we need it to interpolate. And that's why we're seeing so many weird like artifacts there. We need a cleaner way of interpolating this lighting, right? We need some, and it probably wants to be more radial because lighting in general tends to create radial patterns and things, not square patterns, you know? And so I don't really know. I don't really know how we're going to solve that without, again, like, I know the way to write the really large version of it. I just don't know if that's tractable. We could do something where we compute things that do interpolate properly in linear, like maybe like we use I mean, the nice thing about the light P thing is it's sort of a distance value in a sense, right? And so the distance value would give us a way to interpolate these things that maybe makes a little bit more sense. So The thought process I'm going through in my head is that when we interpolate things in a bilinear fashion, right? The thing, if we actually interpolate the output value, so like the color of the light or whatever, or the intensity of it, interpolating the output value, we will get the obvious trilinear artifacts, right? So all of the way in which you will see the edges will look like a sort of, it will look like a bilinear filter. It will have the rectangular pattern of a bilinear filter, like you saw. And it's, trilinear is just doing that in 3D, so you'll get that vertically as well as you would get it in the plane, right? But you see those sort of color washes that end up having cornery artifacts to them, like lines going through them or corners going through them. And you saw that when we were hopping through. You can see it very obviously. And so the question is, if we were to interpolate something that actually didn't have that property, like this is kind of where I'm going in my head, if instead of falling down to 0 and actually producing the output value, if instead we did something that looked more like a signed distance field, so something that was more saying, how far away am I from this thing, that maybe would allow us to create an interpolation that works better. And so, I don't really know if that's something we can construct for lighting, but it might be. It might be. It might be that is something that we could use. Let me run this one more time. Sorry, I want to see. So, given exactly what we have right now, I'm just curious. We have my Turbo C. I downloaded Turbo C, the old Turbo C, by the way, over the weekend. I wanted to take a look at it. So as I'm kind of hopping through here, right? If I am to turn back on that trilinear, I want to look at these artifacts a little bit more closely. I also want to go make sure we're filling our voxel up in as much as we should be, but it's behind my head and I can't see it. There we go. So if we take a look here at the artifacts, and you can see, hopefully, what I'm talking about, how, even inside an area that's relatively subtle, you can see the sort of stair-stepping patterns that you get there. And when you move over to some place that's going to be sort of more dark, like here, or like there, right? You can really see the way it creates a box-like version of this thing, right? So, when you look at a region that doesn't have lighting, you get like this sort of boxy version of the voxel. And it just isn't, it just isn't the sort of fall-off pattern that we want. However, that is because it goes down to 0, I think, in those areas. And it can't really produce, it's not something that can produce a rounded sort of fall off in the area that we're talking about. So what I'm wondering is, could we use an interpolation in that some value we interpolate that is in linear space, but that when you interpolate it with a trilinear filter, produces a more rounded fall off, right? And so thinking about that, like I just want to draw this out and see if there's some way we can tweak it to basically not have to do anything too much more complicated than what we are doing. And so what I'm thinking here is like, what I'm thinking here is like, if you imagine a typical bilinear filter, what we would get at a corner is if we have a 1 value here and 0 values throughout, then if you ask yourself, where is the 0.5 value in here? Then you know, like looking through here, that's going to be the 0.5 value, right? Through here, that's going to be the 0.5 value. Through here, that's going to be the 0.5 value, right? And so as you look at how each of these, oops, no, that's wrong. Sorry, that's going to be 0. That's going to be 0.5, right? And that's going to be 0.25, right? Because looking at how this bilinear would work, right, between 0 and 1, I'd get a 0.5 here. Between 0 and 1, I get a 0.5 here. This here will produce a 0, so when we do a linear between the 0.5 and the 0, or alternatively, if you did the bilinear blend the other way, doesn't matter which way you go, because this is a 0 here as well. This is an 0.25. And then if we kept going on this, right? So if we looked back, one more step, that's an 0.75, right? That's an 0.75 there. And this is a 0 here. So if we were to look at what we would get if we drop this down to 0, halfway in between 0, it's like a 0.625, right? I'll do it on calc to make sure I'm not doing it wrong. Or, sorry, in speed calc. Speed crunch. So if we are talking about a bilinear blend, right, between 0 and 0.75, that would be, what, 0.375? Oops. Right? So if we look at like the kind of the pattern of values here, that's an 0.125, right? I think halfway in between those two, and this would be a 0.375 here. So if you look at these values, you can see that you basically get I think what amounts to a pattern that looks like this. Right? Coming through here. And so that's why you get, I believe, those values of the, just looking at what the values are that you pick up. If you interpolate the light intensity directly and output it, I think you just get these sort of corner looks like that. Specifically because, what ends up happening is the voxel interpolation is just always going in these sort of linear waves. And it's either it's directional in this way, or in this way. And so the question is, could we somehow encode this such that when we interpolate it in this fashion, that's not what we get, right? And so one way to look at it is, if you took a look at what would happen in this bilinear filter if we had filled it with something else. So let's suppose that we took the values that we put in here. And, we wanted a sort of a distance-based fall off or something like that here. So we had a 1 in the light source here. And we're saying it fell off to 0 here. So maybe that's exactly the same. But here, right, we say, no, we're going to continue the distance fall off. So instead of clamping it to 0, we're actually going to let it go negative, right? So if the thing was that the light fall off was 1 along this, then this is like the diagonal, right? So if it fell off 1 here, we would expect it to also fall off 1 here, right? If this is that distance, so how far should it fall off going in that direction, right? And we don't know, because we don't know where the light is necessarily coming from. But if it's a 1 here, then we assume it's kind of coming from maybe that direction or something like that, right? So this should actually be set to a negative value. If we use Pythagorean theorem here and we say h squared equals, a squared plus b squared here, right? If we assume that the light fall off is 1 along here, then effectively what we'd be saying is h squared equals, 1 plus 1, 2, right? So h equals root 2. So we would expect from here to here, this should be like negative root 2, right? I mean, so it should be, that. And so if we allowed the light to fall off in that fashion, then what we would get is something quite different, right? Depending on where you were in here, you would actually drive this would now be contributing. Before it wasn't, it was just clamping essentially. This would now be contributing to the shape of this function, and it would create, in theory anyway, I think, some actual pull, right? Because you would actually be getting some real information from it about how far away you were, right? So the only thing I'm thinking here is, do we need to do something where we actually push those values in as more like a signed distance field like that, where we're basically counting how much light should be in there based on some kind of a location of the voxel sort of a thing. And again, I just don't know. I'm not sure how to do that quite properly, but it's something to think about. And so if we were to do something like that, I guess the question is, how would we do it, right? Let me try and play with that a little bit and see what we get. So first of all, in our sampler, when we have get irradiance, or even when we're just looking these things up to begin with, we kind of need those to be clamped now, because they could be like information that would be negative, like, right? So when we are in the actual fragment code here for get irradiance, and we take a look at the light value that comes in, we compute that light value here by taking the intensity, right? And we use the light RGB and we compute the color that way. If we were to actually take that intensity instead and clamp it so you can't have a negative intensity, I think that would do what we needed to do. Probably. It's worth noting here that we have additional problems now that I look at this, because if you look at what we're doing here too, we have what is effectively non-premultiplied alpha, right? Which again does not distribute properly across box filtering, just the same way like with our sprites. And so one problem that we have there is that if we do want to encode, if we're trying to have a better encoding of the light intensity by using that sort of an HDR format, that in and of itself is also bad, right? So we kind of have a nasty problem there. This just keeps getting worse, right? Because multiplying the alpha, which is effectively the light intensity, right? Multiplying that after the fact, that doesn't actually work. The trilinear, that's an artifact as well. So there's just a lot of really nasty stuff going on here. And I'm not really sure what to do about it, right? Yeah, I'm not really sure. So if we were to take, let's just try a couple things though. I want to play around with it because I'm really feeling like this is incredibly tricky, and I'm just not sure I can think it through in my head and have any really good idea about it. So let's try playing with a couple things here. So let's suppose the light intensity could be negative, right? So in here, what I want to do is take the light value A and I want to clamp that, right? So I want to say, look, this could come in negative. So what I'm going to do is I'm going to clamp that alpha value, right, when it comes in. And so when we're doing that sampling, I want to take and have a way for this alpha value, this light VA there, I want that to be possibly negative. When we actually sample it, like when we're doing this sampling here, it can't really be negative because we're encoding it somehow, right? That doesn't allow for negatives. And so what I would rather do there is say, well, okay, when we look at the light AV, I guess, what we really want to do is bias it first. So we want some way of saying that this is actually a range of light values that can include negatives. You know what I'm saying? So we're essentially saying, look, this number comes in between 0 and 1, but what we really want, right, is we want this to be something that can range between like -1 and 1, right? It's like a binormal number. So we're like doing the bias of multiply the alpha by 2. Now it goes from 0 to 2, and then subtract 1. So if we imagine we encode the alpha that way, now we can encode negative values into our light intensities. And then, furthermore, when we're actually encoding these here on the head end, I believe we've got a thing that does the encoding somewhere. Nope, that's not going to be in here. It's going to be in here. We call like this irradiance pack value. So the irradiance pack value, wherever that happens, it has to respect the way that the light intensity gets folded in here, like what I just said, right? So what has to happen there is when the light gets packed in here, we take a look at the maximum value of all of these, and we then have to say that we are going to normalize by whatever that max value is. And again, now I want this to be able to be negative, right? Which is kind of annoying, but that's what I want. So this can't be the case anymore. We basically have to just say, look, if it's not actually 0, we're going to normalize even if it's negative, and go from there. And so what we need to do here is say, let's take the maximum absolute value. We're going to normalize by that, and then push that back in, right? So whatever the maximum value is, even if the maximum value was negative, then we're going to push that in there, right? And so the problem with this, again, is that the negative values of the light source, like, we kind of can't really allow one to be positive and one to be negative, right? That wouldn't work. So this is actually, in fact, I guess you could do it this way. So we're going to normalize to 1, and if the light happens to be negative, I guess, in one direction and positive in the other, we just get problems there. So maybe don't do that, right? But if we tried doing something like this, we would grab out an absolute value, we would invert based on that, and I guess now I can leave this way. It doesn't really matter. We can do our scaling, and then these light values have to be sort of absolute values, right, at that point. And what we would want to do, in fact, I guess another way to look at this would be, what we want to do now is figure out, was this light generally negative or generally positive? And so I guess another way to look at it would be, we need to take the maximum value, but we need to know what the sign was. This is awful. I hate everything about what we're doing. I just hate lighting in general. This is why I like ray tracers. They don't have all this nonsense. Yeah, I'm really not sure how to look at that cleanly, because all we have coming in here are lighting values, and what we want to do in a radiance pack, right? We would need to have more information to figure out how we would ever make these lights actually come in this way. So we would have to change the way we're computing, and maybe this is still a good idea. Like, I don't know, it could be. But the problem is, I don't even know how to test it without actually writing the entire thing, assuming that that's what we were actually doing. Like, you'd have to base an entire algorithm around that concept. Because in order to even figure out what you should stuff in there, you would need some way of doing that. And I don't know how we would do that. So that's like really hard even to experiment with. We could construct a fake case. And maybe that's the right thing to do. To test it, I just want to make sure this still runs the old way. Yeah. So, maybe I could do that. Maybe I could test it in a fake case first, see what it looks like with that fall off, and go from there. I don't know. Probably worth trying, I guess. So if we were to pretend that we wanted to do that, right? And we ran things this way. So let's suppose we did this. This stuffs things into the voxel directly. I believe I've bracketed that properly. Oops, no, I haven't. Because the problem is this has to happen in the other case as well. There we go. So let me see if I can get this back to just using stuffed voxels. So now we're not like looking at the light probes at all. And we should just be sticking the light probe values in here directly. Of course, the problem is now the light distance fall off is wrong as well. So that's a little bit of an issue. But if we go in here and take what light RC. So if I just stuff this one directly, so let's say this is 3.0F now, which is what it was before, because this is being done inside the UVW space of the voxel. Again, don't really know why we're getting, oh, I do. Because the irradiance pack, we don't call irradiance pack here. So the actual value of the light is not accounted for there. So I suppose here where we do the light C, this should actually be whatever the light intensity is divided by that max. Let me see, is that true? Oops. So that's 0.1 times the max light intensity, and so you can see the problem here is we have to divide by the max light intensity here because we don't call irradiance pack. We just directly stuff the value. Now what I probably should do is get rid of this and call irradiance pack, right? But I'm going to play around with this first, so I don't really want to do that. Let me convert that to an F32. So it's a bit ugly, but we'll go ahead and run it here. And so here is us stuffing the voxel directly, and hopefully that produces a similar little, like, yeah, you can see our little like light sphere that we're moving around now, right? And so my question is, if I was to stuff the values directly and use a bias value in here, so if I go into ZBias program inside renderer, And we actually, like, I just put back in this code that I have here where we clamp, but we actually bias the number. So now that number can be negative. And what we'll get at first now is nonsense because we're not actually encoding the values in that way. We're unpacking them as if we did, but we're not actually encoding them that way. Then we'll get garbage there, right? But if I now go over here and actually try to encode the values that way, so we have sort of a like light fall off here. And what I want to do is, rather than clamping this light value, I want to just let it go, right? So now we allow the light values to become negative. And what I want to do is clamp between like 0 and 1, negative 1 and 1 instead of 0 and 1, so we don't have that hard fall off, and we can actually get negative values in there as well. And then we can sort of play with it as see if we can create an interesting version of a sign distance field there in some way, right? Okay. So we want to know the distance from a thing that we actually are. And so if you look at this, this is an inverse distance of a thing. So that is pretty much correct. It's multiplied by a value, but otherwise it's the same, right? And if we go through and look, yeah, like we've got the total here, we're just summing. So, you know, in theory, I think this should be okay. And so I think all we really need to do there is actually encode the value, right? So we're taking the inverse total here to renormalize this thing, and I guess we maybe don't really want to do that, but when we do that, once we have it normalized, we should be able to map it from negative 1 to 1 pretty straightforward from there. So I think all we need to do is like this. So basically we just clamp these alpha values into range there, and I think that's all we really need. We don't even really need to clamp them, because looking at it, we just kind of divide them anyway. So I think all we really need to do is just do the bias, right? So all we really need to do is say, all right, we're basically just going to do this negative 1 plus 2 kind of thing. So if we just say, all right, we've got a value that'll range from negative 1 to 1 now, and we just want to shrink that down, right? And move it up. Oops. I think that's it. And now it'll be encoded so there are negative values, right? Don't quote me on that. All right. So now there are negative values, and the question is, what did that do to our interpolation, right? And so you can see that it did round it slightly, actually. Interestingly enough, you can see it is a rounder interpolation, right, than we were getting before. Exactly as I predicted. So we are, like, you do get a more round version by not forcing the values to clamp. We do start getting an improvement. And you can see, like, how the actual artifacts now are not so stair-steppy as they were before. They're still not what we want, right? You can still see they do kind of have a stair-steppy-like pattern to them. But they're definitely getting closer, right? They're getting closer to a radial feel. And so keeping the sign in there doesn't seem like a totally stupid thing, but we're still not at the point yet where this would be considered good, right? Like that's not, I mean, maybe it's okay, but as a light source moves, assuming that you would see that kind of a look to it, right? I'm gonna turn this to release mode so I get a little bit higher frame rate so I can watch it at a higher frame rate interpolation wise too. But you can see, like, you know, the interpolation that we do there, even with just using Trilinear, it does make a difference, right? It does make a difference. So let's not write it off yet, okay? Let's see what else we can do there in terms of maybe what, you know, what else might make that work differently. So here, one thing we're doing is we're doing a normalization, right, of the incoming light because we're kind of doing some ridiculousness with directional stuff. Let's maybe say, like, don't do that. You know what I'm saying? Let's maybe actually just clamp it and take that out of the equation for now. And maybe we want to do kind of a let's just stop looking at the different directions of the voxel and trying to, like, just reduce the problem space here down to something a little more manageable so that we're not just, like, flailing around. So instead of this stuff, what I'd rather do is say, all right, let's take this out of the equation temporarily. And let's initialize everybody to effectively nothing. And let's just look at one person, right? So if we were to just say one person is going to directly end up having their sort of light value come in here. So we'll just have light C. And then at the end of this, right, this part we're going to get rid of. So here we'll say, all right, we've got a light value that's coming in here. And all we really want to do now, in fact, I don't care about this. All we really want to do now is clamp that out, right? So I want to clamp this value between -1 and 1 so that it can't be out of range for our encoding. But other than that, I'm not going to do anything to it. So we're just going to stuff down one value that is the distance from the light source for one person, right? And the problem now is since we're only doing one, it's a little too dim for us to really see the edge artifacts correctly. So I'm going to go ahead and amp it up a little bit there, just so we can see, right? So let's go ahead and give it the full power of all 6 directions. That's the wrong place to put that. Let's do that. Okay. And so now if we hop along in there, what I hope you can see is that by getting rid of the way we were filling the voxel, we now have what would be considered an almost correct fall off, even though we're still sampling it the exact same way in the pixel shader, right? Do you see that? Hopefully everyone can see that there. Do you see the quality of that now? And even though this isn't what I was planning on talking about today, what you could sort of see there was just like a real life example of why reconstruction filters matter, right? Not including the negatives, you know, clamping to a value creates artifacts at the border, normalizing inside creates artifacts in the sampling, and what we got was, you know, a really ugly effect out of something that, if we did it correctly, produces actually a quite clean effect, right? Hopefully you can see that there. And so as I'm looking at that now, that reconstruction looks quite good all of a sudden. You know what I'm saying? And so what I think we might need to do here is, okay, let's see how we can, let's see what we can do. If we actually have these sort of light informations in here with the light normal, right? What I'm concerned about is what we know is that if we plug a signed distance field into our trilinear interpolation, we get the correct fall off, right? And the reason for that is because we can trilinearly interpolate just a signed distance field. That actually works. However, if we want directionality in there, right? So you can see that kind of coming in. That is not a signed distance field anymore. And so my assumption is just inserting even just the directionality into it. My assumption is that we will introduce the artifacts literally just by that. So if we now take out the light C value, the multiplier, if I was to just literally have this, so instead of clamp 0 to 1, if I literally just take this stuff and clamp that negative 1 to 1, oops, I'm assuming that that alone will introduce artifacts. If it doesn't, how happy am I? Because then I think we might be almost done. And we can just call it a day. But if it does, then we have to figure out what can we do that would prevent that eventuality from occurring, right? What can we do that would allow us to encode some direction out? Okay. What's the problem here? Oh, right. That's just the light normals. We need to take the light C into account here. So that actually needs to be there. So I'm assuming this won't help us, right? I'm assuming that this is not going to be useful, but I don't know. So here's that. And I'm not sure why we're getting sort of light beyond the boundary there. Actually, I do know why we're getting light beyond the boundary there. So the problem there is that if you have two negatives, so if this was negative, then these negatives will turn this one into a positive. So we need to make sure we actually maintain that sign through the computation properly. Just quickly, though, before we go down that route, looking at the way that this works, I still feel like we have the artifacts already. You can see them, right? It's not that nice smooth fall off anymore. So I kind of feel like, just in general, we already know the answer to our question. We don't really have to go any further. So I think we kind of now need to think about this a little bit more broadly, right? So, what we know is that using just the trilinear reconstruction from the voxel, we can reconstruct a signed distance field, which meant that if the only kind of lighting we wanted in the game was just a radial fall-off light, well, no problem, right? Everything's fine. But in order to have a more interesting lighting environment, we don't just want one radial fall-off, right? So I guess what I think is creating the signed distance field and knowing that we can trilinearly reconstruct it tells us one thing we can do there. but it doesn't really give us much insight into how we would actually be able to reconstruct a lighting direction, because the direction function doesn't have any sort of analog to that, right? Especially not when you're talking about sampled light. So reconstruction with a trilinear filter, if we know that it has to be based on signed distance fields, I'm trying to think if there's any other thing we could do there, but I don't think there is. If we know that signed distance fields are probably the only thing we can actually reconstruct, I guess we're down to the question of, is there a way to take sampled lighting that we have, right, the actual sampled lighting that we want in the world, and take that and put it into effectively a signed distance field construction at voxelization time. Right? And the reason that I'm not particularly optimistic about that is because if we want to, we need to know stuff like what direction the lighting is coming from. Right? We kind of need to know that. And to be fair, there are some interesting things we could think about doing there. If all we had was signed distance fields for the amount of light, one interesting thing to think about is you could imagine saying that the direction the light is coming from is just the gradient of that signed distance field, right? Because the signed distance field has a well-defined gradient on it. And if we said, well, the direction that the light is coming from, it has to be the direction of the signed distance field, and we're not going to encode things like east, west, north, south, and down or anything like that, or we still are, but we're going to consider each of those things to be a signed distance field where the light direction is based on the gradients of the signed distance field, then we know that would be smoothly interpolated from the trilinear filter, right? In theory. And so I really do think we need to think pretty carefully about this because, again, mathematically speaking, I don't know anything else we can do other than a signed distance field that would interpolate properly on the trilinear filter, right? And maybe that's just me not having thought about trilinear filters enough. Maybe there are other things we could do mathematically that would add correctly in there. But I feel like the trilinear filter, the only thing I recall ever being mathematically reconstructible from the trilinear filter is a signed distance field. I don't know what else we could really do. Maybe there's something I'm forgetting, but it seems like it breaks down to a fairly mathematical process of what can we represent in signed distance fields, because those are the things that will be reconstructed without artifacts. How do you feel about that? I guess I don't know how people on chat feel about that, but that's sort of what I'm thinking. And so if you take a look at the equations that are on the screen right now, right, you can see what we were sort of doing there is we were saying, like, look, what direction is the light coming from? And that tells us, our normal to the light source, right? You can see us computing that there. And we normalize that so we have like a general direction, and we're saying this is where the light is coming from. It's coming from over here, We then encode that. We were trying to encode sort of light information by saying, all right, let's distribute that light to the 6 faces of the cube by saying whatever the lighting normal is, that's going to tell us how much contribution should go into that face of the cube, right? And that, so what you can see, I mean, again, just want to sort of highlight the math here. What you can see is this part of that equation right here. Right? This is the normalizer 0 part. I'm going to go out on a limb here and say that's that was where the artifacts were coming from there. And the reason that, I suspect that is because if you look at all of the equations that we have on the screen right now, that's the only one that really has a nonlinear function in it, right? And so what we're doing, so a trilinear filter, right, is effectively reconstructing something linear underneath it. And so we can expect to be able to do a linear sign distance field, should be reconstructible, right? Generally speaking, should be reconstructible if we have only one thing that is being used in a normalized fashion, which would be this length function right here. So one thing that's a distance from a point, we should expect to be able to reconstruct it, and we did. But here we've got a second thing that's being normalized, which is this light normal vector, right? So thinking that through, I guess I wonder if we're gonna have to actually work out the math here and figure out should we expect to be able to add two sign distance fields together in that way? Because that's sort of effectively what this is doing. Oh, this is not really a sign distance field either. So bear with me for a moment. Let's suppose here we were to take out this normalization entirely, right? So instead what we had is we had the direction to the light source, and we looked at that as a separate parameter that was going to be coming down separate from the actual light information somehow, right? And so rather than doing this the way that we were doing it, instead of putting this piece of information, that light direction, in there, well, in fact, you know what? Let's think about it in even another way. Let's suppose we were to encode only the light intensity here, and then we actually, in here where we packed the color, we use the normal for that, right? Let's say. I'm just throwing that out as one one thing we could try here, just to see what happens if we try to get that out. So we only have, in the alpha channel, we only have one thing that's a sign distance field being reconstructed, and then the RGB we put the other stuff. Is there any way we could sort of make that work? Again, probably not, unless we actually allow this to be signed as well. So I suppose as I'm kind of saying that out loud, I'm thinking, no, that's not actually correct, because the coloring value of it, wouldn't actually work there, I suppose. So as I say that, maybe that's not the best idea. But again, yeah, just thinking about this through. So what if we were to have the direction be something that could be reconstructed correctly as well? That's the only thing I'm thinking, because you could see adding that directionality in there, right? We immediately got some artifacting back, and just looking at the difference, like look in the interior, you can see all the ringing and stuff that happens in there. And when we turn that off, right? So when we don't have the light information in there, so if we literally just have light C. When we literally just have light C, oh, well, actually, no, that one, now I'm getting that artifact back. Okay, that was pretty instructive. So what happened there that was the problem? I thought that we had that reconstructing properly, but now that I look at it, it's wrong again. Is that just because it's too bright? So did I just fool myself into thinking we had reconstructed that properly? Which maybe I did. Maybe I spoke too soon. But I would have thought, yeah, well, we'll see. So let's suppose we turn the light intensity down a little bit there. Or I guess what we did do is we only had one of them, I guess, is one thing, what we did there. So let's say we take light C and divide it by 6. Just want to see what's up there. If that's the case too, it may just be that, again, we don't have the range for it, which is entirely possible as well. And the artifact is actually coming from the quantization. But no, like, that's totally busted, right? So I guess let's take a look here. If I get rid of this and we nuke the north, down, up, out of here, is it just the fact that we have multiple directions coming together that's producing those artifacts? So going ahead and increasing the light intensity here. So, okay, so it looks like actually I was wrong about that. I'm now starting to wonder, is there something weird in our shader? Maybe, like, I clearly didn't think about this problem correctly, because what you can see there is that actually, as long as it's only one of the channels, it's fine. And if you stuff all the channels with things that should have worked properly, you don't actually get that. And so the reflection function in here seems to be causing more damage than I anticipated. So inside the ZBias program, just taking a look at how we're doing that, I'm curious here what's going on. So in here, you know, when we take a look at how we're computing the, you know, here's the interpolated value. This appears to come through correctly if there's only one of them. When we actually go ahead and compute the rest of it here, so we've got, like for example, you know, doing the reflection, normal, the inner product, and so on. That alone seems to be enough to create our artifacts. So for example, if we were to drop the light down one, I'm just curious again. So and allow both, say, well, let's try, for example, let's try both west and south. And that still looks fine to me. I don't see artifacting in that reconstruction. Let's try, so what I'm doing here is I'm just trying the positive versions of it, right? So none of the negative facing versions. So let's suppose now we do the west, I'm sorry, the negative facing versions. The west, the south, and the down. And I guess, to be honest, I do start to see the artifacting kind of coming back there. And so I guess what I'm wondering is maybe I'm just wrong. My intuition was wrong about that, which is, you know, pretty easy to have happen when you're doing something like lighting. I guess what I would say is it looks to me like it's really our box sampling that is the problem there, right? Because if we do allow sign distance field interpolation on our light values there, we are okay. It really looks like the only problem that I'm seeing is because of the box-based lighting. Again, good to know, right? This is exactly why we need to do this, to make sure we know what we're doing here, because it's not obvious. So let's suppose I switched back here. I want to know now if I clamped my light values so that they actually fall off, so that they don't have the negative values. Is it possible that we didn't even really need that changing it to a sign distance field was in fact unnecessary, right? And I'm not sure. So again, looks pretty nice and smooth there. If I now go and clamp these values to 0, so the fall off becomes, you know, truncated, I just want to see, do we get the banding or don't we? Okay, so actually, I didn't really even need that. I mean, it is true that it looks better, and you get, well, you know, no, I guess I would say it's pretty bad. So the sign distance field, I was going to say it's not that bad without it, but it is kind of, actually. The more I move around, it's not so good. So I do think the sign distance field part probably is important. We probably need something that can be reconstructed. If we stay with the trilinear filter reconstruction, it does look like you really do want this. But it looks like, and maybe I'm wrong, but it looks like interpolating box directional ain't gonna cut it. And again, now maybe I did something wrong. So maybe I've got a bug in some other part of the math there. Very possible. But just looking at the quality of this versus the quality of the box space interpolation, it's just, I mean, to use a bad lighting pun, it's just night and day, right? I mean, that looks perfect to me, basically. I couldn't ask for a better radial fall off than that. In practice, it looks great. Everything looks perfect. But once we started putting in those box directions, when those get summed together, it was not good at all. Even though each one was being summed independently, those directional values just did not compose properly. It didn't look like, right? And so I think what we need to do is take a step back, and we need to figure out how are we going to interpolate light directionality better than that, because that's not sufficient. It's what it looks like to me. And unfortunately, I don't know. Like, I don't have a magical way we could really do that. So we're going to have to think about that. And it may require changing to a different basis, right? It may require using maybe a spherical harmonic basis. It maybe requires us to do, you know, bent normals would be another option. I don't know. I'm not sure, but just looking at that, I don't think the reconstruction is very good with boxes. And we're going to need something that could, if we're going to use trilinear filtering, we need something that a trilinear filter can actually reconstruct, right? Now, one thing we could do is say, maybe we just have two light directions or something, or, you know, what amounts to basically like be a normal, because we can interpolate that. I wish I had a better intuition. I don't actually know what happens to spherical harmonics under a trilinear filter. That is something we would probably have to investigate. We'd have to actually write out what's going to happen if you do that reconstruction, because I don't really know. I do wonder kind of offhand, what would happen if we just reconstructed the normal, right? So if we actually said, like, what we're actually going to push through here is just the normal to the light source, and we store an average normal, right? And maybe we sort, you know, we could sort two normals. So, you know, we've got some kind of lighting information that stores, you know, just various values in our RGBA. And you can imagine storing, so like two normal directions, so the like primary and secondary lighting directions. Or even just maybe one normal direction and one color, or sorry, one normal direction and two colors. So basically, like, what's the primary light, and then what's the secondary light? So what's coming from behind that? You could also imagine doing something like that. And spherical harmonics are sort of like that, but they're non-direct. They encode the direction into the coefficients directly, as opposed to having a secondary piece of information that tells you. What I'm most tempted to do right now, in the amount of time we have left, which I don't think is much, it's like 20 minutes or so, would be maybe like I would like to go in and see what would happen to just interpolated normals. Can we reconstruct those with the Trilinear filter properly? Because we know we can't reconstruct them exactly, but what we do know is we can linearly interpolate them and then renormalize them. And furthermore, we also know that we could encode them if we wanted to. We can encode directions as quaternions if we want to, and then the reconstruction is even better, right? Because the reconstruction would be based on half angles instead of angles, and we'd get even less distortion from the blending of the two, right? So we have a lot of options there, and I guess what I would say is I am interested, to know. I'm interested to know. I'm also a little bit wondering why, with our light fall off here, we never seem to get down to black. What's going on there? Is there some kind of a what's happening there? Did I mess something up there? Because we should be getting no lighting. What are we stuffing in here? So we got east, south, north, down, up. Those are all 0, right? So if we said west A equals 0, we should get nothing, right? This should just be black. Entirely black. And we're actually getting some light. So I've got some kind of an encoding bug here. And I'm not sure what it is. Right? Because here we're stuffing all values to 0. So that 0 is not actually a 0. I assume that's because of the way we're doing the encoding here. Actually producing a value slightly above 0. Right? I mean, if you think about what's happening there. So if this were to be actually somewhat negative, something's weird about that. Because we have a clamp 0 to 1 here, 2 times the light value alpha, minus 1, right? And so what we should be getting, if this thing was 0, is we should be getting full negative 1, right? Now we're biasing it here, so we can't get full 0. But let's suppose I actually sent down negative 1 everywhere. Now we should definitely clamp to 0. Ah, okay. And how about 0.5? All of these should be black. We should see nothing on the screen. All right. So that's just because our 0 handling is not correct, right? When we're actually at 0, we're actually producing a value that doesn't decode directly, right? So it's actually, oops, I didn't mean to launch the profiler. So when we encode that, we need to encode something actually that will map to 0 properly. And when we're encoding it this way, what we end up with here, right, is 0.5 times 255. So like, just to show you what's happening there. So we're ending up with 127.5, which of course has to kind of be rounded one way or the other, right? And so I assume that the zero value is actually 128 when the graphics card unpacks it. And so I would assume what we're getting, well, or it's 127, I guess. I guess I don't know. We'll have to go look at how the graphics card would unpack that value. Let's think about this for a second. I'm assuming that the graphics card unpacks the value as when the light value comes in, it's going to take, you know, something it gets like if the 127.5, if we round that and we get 128, and that's what we store. I'm assuming it's going to divide that by 255 and get out some value, like that's 0.501, right? So when we take that value we're going to unbias it, right? So we're going to do 2 times the answer minus 0.5. That's going to give us, oops, that's not what I wanted. 2 times answer minus 1. That's what I wanted. And then we're going to multiply that by the max light intensity, which we said was 10. And what you can see there is we actually get a fair bit of light out of that. Now, one thing that you may notice about that is maybe that means this encoding in general is not precise enough and the max light intensity can't be 10, right? Not with an encoding that small. And that could be part of it too, right? Like that could be the fact that encoding is not good enough. Could be another way that we're seeing that lighting reconstruction be bad, but you know, we can reduce that, and we can also try to handle our zeros better. So what we could try to do there is say, no, we want this to map to exactly 0, and so maybe we need to include the biasing in there. So let's take a look at what the GPU actually is going to do, like what the exact unpack equation is, whether there's a 0.5 bias in there or whether there isn't, I'm not sure. Like whether it's doing this exactly or whatnot. I assume it is doing that exactly. And so what that means is we would actually want to subtract that value from it, right? We would want to, when we do the answer minus 1, we would actually want to do the answer minus 1.03 blah, 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 right? Like we would want this, right? Does that make some sense? Because we care a lot about that 0 value, and we want to make sure that it actually falls off to an actual 0 value. And there's a number of ways we could do that, but that's like one of them, right? Oops, what did I do there? There we go. So we can just adjust for that bias, and that's not a huge deal, but we definitely want 0 to be 0. And then the question is, are we too... you know, how rigid is our stair step there? But it looks, again, it looks pretty darn good, right? In terms of reconstructing a radial fall off, you know, I'm pretty darn happy with that. I'm not sure what you would really want if that wasn't good enough for you, right? That looks pretty nice to me. Doesn't it? I think it does. Yeah. So I think that's pretty good. I have no complaints about that. And just looking at the edges, they all look pretty nice. They look like they fall off along the geometry the way that they should. And I would be totally, you know, I would be totally fine with that. So then from there, right, now we just got to figure out, like, okay, so what about doing something like encoding the normal direction, right? Because one thing you can see here, right, is that the normal is just hard set to west. And so what you see is, as I walk over to these, you see no lighting on those faces because, hey, the lighting is directly opposite them. You come over here, you see lighting on these faces because the lighting is coming directly from the correct direction. So these are the brightest they can possibly be. And then you got like some limited brightness in the areas of things that are sort of facing more orthogonal to those, right? But the question is, what if we want this light to actually have some directionality to it? And you can see as I move it around, what I would like to say is this should be in the direction of the light, and this should be in the direction of the light. They're both pointing towards the light. The thing that's pointing away from the light would be like these faces over here. Like those are pointing away from the light, right? And so they shouldn't have anything, but these faces here definitely should. And so if we want to start encoding the direction of that light in there, what I was wondering is, what if we encoded just the direction and tried to reconstruct that with the Trilinear filter by taking the light direction, doing a Trilinear filter on it, and then normalizing it, right? So we are trying to reintroduce the nonlinearity of the interpolation. It won't be speed correct because it will be doing a linear interpolation that then renormalizes. So what you'll get is that standard sort of lerp versus slurp difference there. But it's the worst possible case because unlike slurp, which is typically quaternion, we're talking about the slurp of a vector, which would be quite a bit different than just a normalized lerp of a vector, if that makes sense. So I'm not sure if that would produce artifacts that we don't like either, but what I would like to do is I'd like to see it, right? I'd like to see that for myself. So let's suppose we were going to shove some crap down there. What would that look like? What I'd like to do is let's take advantage of the fact that we have some samplers here, and what I'm going to do is just try to jam it down the samplers we currently have, right? So instead of this stuff, we're not gonna encode these light values anymore. We're going to encode that west value, which we did, and then the light n value. We're going to do all this a little bit differently. So I'm going to comment these lines out. These lines go away. So actually, let me do it this way. So these lines will go away. We're only sampling the western direction now of our lighting. And that should produce no change now, right? Because the other ones weren't providing anything. And so all I really want to do now is change the way that I am like reconstructing the light west normal. So the light west normal, instead of being what it was before, where we just know that it's coming from a western direction, what I want to do here is actually grab the light west direction out of a texture. So we'll see that what we did is, inside light sampler east, I'm going to actually have the light direction encoding. And so we're just going to grab that out and use that. But I would like to... I need it to be able to be positive and negative, right? Now what I'm going to do to give myself a little bit more resolution here, because I think we can cheat a little bit in this point, is I'm going to take two of these and subtract them. I'm going to take, in fact, let's do north and south. So north minus south. So we can encode 0 to 1 in our north and -1 to 0 in our south, flipped. So this will allow me to do full -1 to 1 without sacrificing any precision of the 0 to 255 encoding of the normal, which is already not that great of encoding of a floating point number, but it's pretty good for only numbers from 0 to 1. It's some resolution there. So let's go ahead and encode that. We know this is the light normal. Oh, and by the way, after we do that, I would like to normalize it. So light west n equals NOS light west n, right? So I'm going to normalize it. We can try it with and without that normalization. So now what I'd like to do is encode that correctly. So in here, we do all this garbage and whatever. I'm actually going to add some modification in here. So what I want to do is say that the light normal, which we have, I'm going to take and encode using the BGRI pack function here. In fact, let me just do this. So using the BGRI pack, what I want to do now is say, well, you know what? The alpha value is going to be nothing because we don't have any alpha value that we need to come in here at all. And then the north and south is going to pack in the information about the direction of the light source. So what I'm going to do is I'm going to take and I'm going to do a clamp 0 to 1 of the light normals x, the light normals y, and the light normals z. Like so. And so what we're doing here is we're just saying, look, let's go ahead and give us the positive version. And then what I'm going to do is I'm going to do the same exact thing for the south, but for the negatives, right? So what I want to do here is clamp the negative version. So again, I'm just saying, look, take the positive component of the normal, stuff it into the north, take the negative component of normal, stuff it into the south, and then we'll reconstruct it by just adding those two together. But, you know, we're subtracting the south because it was negated to begin with, right? So that should allow me to reconstruct the direction of the light somehow. Of course, we have a shader error here, syntax error, unexpected identifier, light west end, comma, or semicolon. Right you are. Sorry about that, Mr. Shader Compiler. And so let's just take a look at what happens if we interpolate that normal direction now. And again, all I want to do now is just see what I get for artifacts, right? So I'm trying to see what kind of artifacts I get when I do that interpolation. And now what you can see, hopefully, is like, let's say I stand there. What we should see is that the reflection against the back surfaces should be nothing, right? Because the light's coming from here, and so that back surface should be nothing. Looking at how it reflects on the light, yeah, I mean, that looks pretty good. I don't see any artifacts really. I'd have to squint pretty hard to look at those, to see those, right? And so I would consider that kind of a limited success, to be honest, right? And, you know, don't forget we also have some kind of random crap going in there that we probably would want to get rid of here. If you remember, so the way that we were doing our clamping here is the sort of contribution of the light source. When we multiply in the light direction that it's coming from, we're including this sort of like biased version of that because we had plate-based lighting. And so if we were to sort of say, well, you know, maybe we're actually going to do something where we reconstruct light directions a little bit more precisely, we probably wouldn't do that. So we'd probably say something more like just do the direct version of this. And that's going to be more representative of what we would see. So that would look more like this, right? And again, no real artifacts there that I'm seeing. Pretty much works exactly as I would expect, right? So hey, this turned out to be a lesson for all of us, including me, in Reconstruction today. I had not really thought about it much because, you know, we hadn't done anything with that trilinear filtering. But if you look at the Reconstruction, we're able to reconstruct those functions quite well. The cube was not reconstructing well. Now, that may be because we just didn't think of the right way to reconstruct the cube, but it makes me feel like what we really want to do is take a step back and say, okay, what can, like that reconstruction looks so nice, what can we shove down there that would reconstruct with a trilinear filter? Because it sure seems to work okay, right? It does seem like the trilinear filter will reconstruct this lighting well. So let's just forget about the box idea, because maybe that's stupid, and let's find something we can reconstruct. Maybe that's spherical harmonics, maybe that's not, I'm not sure, but you know, that's I think what we're looking at here. Let's go ahead and go to the Q&A. Oh right, it's a Saturday, so the mouse doesn't work on Linux. What was I thinking? Oh, Anka was asking, are you going to upgrade the stream forker to the latest one you and Alan are working on? So no, I branched to my own editor now, and it's on my code base specifically, so it's kind of a separate thing. I only want to use stuff on stream that's like available to the general public, if that makes sense. So I'm gonna stick with the one I've got. For us latecomers, what helps smooth the voxel-like outline of the lighting? So this is for people who missed the stream. So there's a couple different things, and basically what I would say is the high-level overview of it is that we kind of have to remember that whatever we choose as our reconstruction scheme on the back end, so in the fragment shader, we have to reconstruct lighting from some crappy version of the lighting, right? Because the good version of the lighting is everything's ray traced always everywhere, and you have, you know, a machine with 20 RTX 2080s in it, and you can actually just run real-time full ray tracing on every scene all the time in real time, all with no smoothing, right? In some magical world. Since we know we can't have that, because even high-end systems today can't do that, right? You don't do full ray tracing of everything, every frame with no smoothing. You pretty much need to have some way of taking your lighting and reconstructing some low-quality version of it into something that looks good. And that reconstruction itself is a critical part of the algorithm. So there's the sampling of the lighting in the first place, and that's critical because it has to be done quickly, and you want it to produce sort of diffuse lighting effects and light propagation that helps make the game look nice. So that actually obviously has to happen. But then the other thing you have to do is you have to be able to reconstruct the lighting from whatever you sampled. When you push it down to the graphics card, per pixel, you've got to resample it because you have to reconstruct it. You don't have the actual lighting information at every pixel. You only have the lighting information at some sparse set of locations, and the question is, what can you do to reconstruct the lighting in a way that looks good? And you almost don't care about accuracy too much. I mean, you need it to be somewhat related to the actual lighting. But the most important thing by far is that the reconstruction has to look good, right? Because if the reconstruction doesn't look good, it doesn't matter how accurate it is, it will be ugly. And the most important thing in a game is that it not be ugly, right? It needs to be attractive looking because the whole point of the graphics is that people want to play it, right? Does that make sense? And so what that means is that in the reconstruction, we have to consider what things can our reconstruction reconstruct well and which ones can't it. Now, there's a question of which kind of reconstruction you want to use, because there's lots of ways we could do reconstruction. We know that the graphics card does trilinear filtering on voxels very quickly, right? So in terms of reconstructing a 3D effect like lighting, if we put down a low resolution voxel and we ask it to reconstruct the lighting with a low resolution voxel, we know the graphics card can trilinearly interpolate values quickly. So the question for today was, if we don't change that, right? So we stick with just trilinear filtering as the reconstruction. You know what I'm saying? What could we do? What values could we push into our voxel that a trilinear filter will reconstruct pleasantly, right? And so one thing that we know that trilinear and bilinear filtering can interpolate properly is a signed distance field. A signed distance field is basically saying for every point that I specify something, so each cube of the voxel, or well, in our case they're sort of right rectangular prisms, but you know, for each rectangular solid in the prism, in the voxel, we know we can only have one thing there, and let's say it's at the center of the voxel. So we know we've got sort of a regular grid of sample points. If we trilinearly interpolate those, we know that one thing we can do is if every point in that voxel was just recording the distance from something, right? Some distance. And the distance was continuous. Then when we actually interpolate that, we will get back out in a correct answer, right? We will get back out and actually correct distance from the thing. That will happen, right? And in order for that to happen and to look proper, though, we can't clamp to 0. We could clamp to 0 if we didn't care what the light was at 0, but we do. So what we need is we need our range to extend past 0. We need to have what is effectively resolution out in the dark area, right? And what I drew on stream was showing the fact that if you look at what happens in a region at the edge of the light source, you have like a 1 value or a positive value, and then a bunch of 0 values around it. That's not sufficient to reconstruct what the shape should have been there. So the reason you actually need a signed distance field is you don't really care about the sign of it. What you care about is that you have resolution of your distance field past the end of the lighting. And we know the lighting ends at 0 intensity, so that means we need things that define what happens out in the negative intensity. Because at that interpolation border, we need to know what it looked like, right? Now you could equivalently do this by just saying we don't have a signed distance field. Our distance field goes from 0 to something, but our actual where the lighting ends is at 0.4, right? So black is 0.4, and 0 is actually super black, right? Super no lighting. This is related to just general isosurface sampling. So you could say like our isosurface is now at 0.5. So it was 0, 0.5, and 1. Darkness is at 0.5, so we have full resolution back. We can slide where that is anywhere we want. We could say that pure dark is 0.2. And so 0 to 0.2 is the boundary area where we encode what happens in darkness. And then we use the 0.2 to 1.0 to encode the light. That's probably smarter. We probably don't need full resolution in darkness that we need in lightness. So we can actually play with that quite a bit. And that's something we should tweak. But if you look at what happens, if we treat it as a signed distance field versus not, so meaning if we have resolution in the darks or we don't, if you look at what happens there, so remember this is what the quality of the lighting as it stands, right? And it looks pretty darn nice. Then we go and we look at what happens if we don't use that signed distance field. So let's say I suppose I clamp these values. We can actually just watch this happen. So there you can see sort of the outline, and it's nice and spherical, right? And everything looks kind of pleasant. If I go here and I change these clamp values to 0, now we've lost that resolution. So now the resolution that we had in the blacks is gone. And if we go back and look at what happens when we recompile and reload into that, did that actually work? It did not. I was like, that still looks fine. That's because it didn't recompile, because that needs to be, oh, there we go. And so now if we recompile and we wait till it to reload here, what we'll see on the border is, do you see how it becomes rectangular, right? Can you see all those rectangular artifacts that are now in there, right? And again, that's just because now we don't know, it's just zeros out there. So the interpolator doesn't know what it's looking at, and it creates hard lines because it doesn't know what should happen in those extra bilinear samples. It's like taking 1 or 2 of your bilinear samples out of the equation entirely. And it really doesn't work to do that, right? You need all 4 bilinear samples to correctly tell you what the function looked like when it passed through that area. And so restoring that ability gets us what we need, right? And now you can see kind of, right, that we get that nice smooth interpolation. This is the same thing, by the way, if you've ever seen, like originally where we did this for texture interpolation. So, all I'm doing is literally like this, right? This is exactly the same. It's exactly analogous, right? So if you look at like Valve, I would consider this a fairly seminal paper on this kind of reconstruction. If you look at what Chris Green did at Valve, he was a Looking Glass person. He wrote. If you don't know who Chris Green is, it's because he's not a self-promoting kind of person. He is probably one of the most like accomplished graphics people. He wrote the first texture mapper you probably ever saw in real time. And he was the person who wrote the texture mapper for Ultima Underworld, the first like really full 3D game that existed in the world, for the most part, at least that you ever played on a PC. And that's him, right? So anyway, if you look at what he did here, this is exactly the same. This is what he was doing. He was saying, look, when we interpolate using a bilinear filter, if we're actually interpolating the color, the problem is that that doesn't interpolate properly at the borders. So if we then just alpha test something for like a decal, it looks like crap because it's basically just like using the stair-step pattern. You can see it, right? And so if what we do instead is we actually track what happens outside the region where we actually have the full brightness, what you end up with is something that does reconstruct properly, and then alpha test works exactly as you would expect, right? And so that's all I was doing, is exactly that. I was saying, look, let's track what happens outside the bright area so that we can correctly reproduce that fall off. Now, like I said, we don't really need all of this resolution, right? We don't really need to have, like, we can clamp this and do it in a different way, right? So instead of -1 to 1 here, what we could is clamp it to the range of like -0.2. And I'm going to put a to-do in there even for that. And all I'm trying to say there is like, look, you really don't need the same resolution in darkness as you do in the lightness, because all we need to do is make sure that our borders are nicely clean. But after we get outside that border region, we don't need to know anymore. So we just need to be able to capture the steepest possible fall off at the border, and once we do that, we don't need the resolution anymore. So we probably want to bias that away. Spiny said, what's the reason you want to keep with the light probes approach instead of using light entities? I guess I'm not sure I understand the question. What is a light entity? I mean, obviously I know what a light probe entity is because that's what we're doing. We have those light probes are light probe entities, but I don't know what a light entity is. So Spiny says light source. So yeah, again, I guess I don't really understand. So just to recap, the lights can be placed in the world wherever you want, and that's separate. So there are lights everywhere, right? Anywhere you want, you can just place light sources. So any entity can emit a light source if you want it to. That's there. But that really doesn't have any bearing on us how we actually have to compute what happens to the lighting. So the idea behind light probes is that light probes don't put light into the world. Light probes are there to say where we're going to simulate light bouncing around, right? So the light probes are ways of saying we're going to capture what the lighting looks like in this area from indirect light sources, like things that bounce off walls and all that sort of stuff, right? And that's what a light probe is. It has nothing to do with where light emits from. Light emitters are totally separate, and they can be anywhere. And they're unrelated to the light probes, right? The light probes are where we compute lighting, not where we emit lighting. Emission happens anywhere and on any entity. And we don't care, right? We don't need to restrict where light is emitted, because emitting light isn't necessarily expensive. It is in some sense if you want to bias your sampling to make sure that you count for them more potentially. But in general, I guess I would say the emission is mostly not the problem. It's the figuring out, doing all the raycasting to determine where that light bounces, and that's what we need to restrict, which is why we have light probes instead of doing it per pixel, right? Because doing the actual light transport per pixel is prohibitive. Is one way to think of it, right? Because there's 1920 by 1080 pixels on the screen at a minimum before you even count like multi-sampling or transparency. And so if you just think about how many points that is, where to simulate the bounce lighting, it's just way too many. So the light probes are a way of reducing that down because we don't need the light to change too dramatically, if that makes sense. Like from pixel to pixel, the lighting probably shouldn't change too dramatically. Could you explain about the real-time fluid simulation for games? For example, how to simulate swirling smoke. Have you read the paper by Yostam on the real-time fluid solver for games? It's really interesting in my opinion. So I guess I'm not sure which Yostam paper you're talking about. Are you talking about the original paper called Stable Fluids? Or are you talking about a different paper? I mean, I can bring it up for you if you don't. So you're talking about this, or you're talking about a later paper? Yostem is, pretty prolific, or at least he was. I guess I don't know if he is anymore because I haven't read any Yostem papers recently. But he's made a lot of contributions to Gastro, so I don't know which paper you're talking about, but this is the one that I thought you might be talking about, so you'll have to tell me if it is or not. This paper, okay, let me click on that link there. Okay, yeah. So this is basically the this is basically the same paper. It's just a tutorial version of the paper, basically. Yeah. Yep. Okay. So yes, we are talking about this paper. We're just talking about a tutorial form, basically, of this paper, more or less. So I guess what I would say is not today would be the answer. This is a pretty in-depth topic. So what you have to remember is that fluid solvers, trying to think of how to give a high level overview here. Simulating fluids was a very challenging problem in computer graphics for a while, largely because it requires a lot of computation. And if you think about what's actually happening in fluid simulation in the real world, it's trillions of molecules that are all moving around to form a sort of blob, right? And the thing that we usually get away with in computer graphics for solids is, rather than tracking all trillion molecules in the 3D cube that's bouncing around your screen, we just remember the general outline of the cube, right? We make a boundary representation that just says, here are the 6 faces of the cube. And then we just simulate it as one continuous shape that everything in it moves together, right? One like rigid shape. And so this drastically reduces the number of computations by like 1 trillion, right? Because instead of simulating every molecule in there, we just simulate one molecule effectively, which is the cube, moving around, and we just place all of the rest of the molecules automatically, because we know where they exist, relative to this thing. So it's really simple, right? It just turns this really dense, ridiculous problem of simulating the physical behavior of molecules into something incredibly simple, because we know that all the molecules just move together, right? And it's a reasonable simplification for our purposes. Now, when you start to talk about things like fluid dynamics, which is like compressible fluids like smoke, which means that they can be denser or less dense depending on where they are, or incompressible fluids like water, which is to say that water can't really change its density is the same everywhere. And so you push on one end, it comes out the other end. It doesn't first create a dense version and then slowly, decompress. You end up with a much more challenging problem, because now you need some way of actually simulating what goes on throughout the entire fluid, right? The entire shape. And you need a way to represent the fact that its boundary is continuously deforming, right? The shape, the contents of this thing, it's constantly changing what it looks like. The stable fluids paper was the first paper to apply what I would call a backwards integration method, or a backwards Euler. I don't know how you want to talk about it. There are terms for these sorts of things. It was the first time that anyone in graphics had ever applied, as far as I know, a backwards Euler integration method into something like fluids. As a result, the fluids themselves didn't explode anymore with large time steps. Previously, things were forward integrators. These are integrators that look at the current time step. Backwards and forwards integrators, again, a whole huge topic. This is why I said I can't really tell you much about it today, but I'm just trying to give you the overview. Backwards and forwards integrators, the only difference between them is, in one case, a forwards integrator says, what is my state of my system, what does it look like now? I am then going to take whatever my time step is, and I'm going to move everything forward by that time step using a physical simulation. Right? That's forwards integration. Backwards integration does sort of the opposite of that. What it does is it says, all right, I'm going to imagine that there's some hypothetical future state. I don't know what it is, because that's what I need to find out. But what I want to do is I want to figure out what future state would have an inverse physics simulation that would arrive back at the current state that I have. Right? And I know this sounds kind of counterintuitive. It's like, wait, what are you talking about? But the difference is actually pretty straightforward. One is a solve, and one is a expression, right? And just to give you a little bit of perspective on what that is, I can draw that really quickly. I don't want to get too far in the weeds here, but the easiest way to think of it is, let's suppose I have a position of a particle, right, P. And then I have some time step, right, that I'm going to take, right? This is my time step. So this is really a delta time, right? So I have some time step I'm going to take, and I know that like I got some physical crap happening, like a velocity or something here. And so like the new point is going to be some time step times the velocity, right? Or something like this, right? So I got a particle, it's moving through space, I'm going to move it somewhere, it's got a speed and whatever, right? Normal physics stuff. Well, normally the way we think about writing this in games, if we don't know very much about physics, which is most people who write games, we would end up with something that was like, okay, to compute the new position, what I want to do is take the old position and I want to add t times some like velocity vector that is simulated with physics, right, or something. So this is like not as simple as it looks. Like it's not just a vector. Usually there's some physics simulation with bouncing and speed and acceleration and whatever else. But it basically comes down to something that looks like this equation: old position plus some time variant thing equals new position, right? And this is totally fine for some things like particle physics effects and things like we're doing in Handmade Hero that we don't care too much about. We'll write this equation all the time, and it's fine. But once you get to physics equations that have sort of stiff parameters to them, things that can explode, things that can go like really off the rails if you have things that have too much force or too many forces acting on them, or who knows what, get bad feedback loops, these things can explode pretty quickly, right? And so what backwards integration looks like is it's a little bit different, right? What it looks like instead is saying, well, instead of doing like a forward computation here, what I actually want to do is say, let me try to phrase what I'm actually doing in terms of solving for the actual change instead of just prescribing what the change actually is, right? And so what you tend to do instead is you see stuff like saying, well, what if I said that I had a p prime, right? So I had like my new state, and I wanted to say that if I took away, right? If I took away the actual if I was to say, how would I get back to the original state that I had? So I did an inverted look back at the physics. What would the solution to that equation be, right? Because I don't actually know this value, right? So instead of just looking at it as something that's pre-solved, right? That's looking at it as something that is just an expression where I already know this and I can compute this directly, so I just literally update the thing. You instead look at it as a solve of what would this have to be in order to make this equation be true, right? And you can think of it sort of as saying, well, and I agree this is really hand-wavy, so I apologize. I should probably think about how to present this in a good way. It's just not something I work with very commonly, so I'm not sure how to give it the 5-second overview. You know, things that I'm really familiar with, I can bust out a good explanation for quickly. Things that I'm like only dealt with a little bit in the past, they're harder for me to do on the spot. But you can think of it as sort of, you know, if you imagine a diagram, and I said, all right, look, we're going to have some orbital dynamics thing, right? And it's like, it's a thing that's going around a circle, right? So I'm orbiting, I'm a planet, let's say, I don't know, here's Earth, right? And I'm orbiting this planet, I got my satellite, it's great, right? Everyone's happy, it's wonderful. So as I'm orbiting this planet, what I know is that if I imagined that I could just do the like cosine theta, sine theta, pre-integrated version of this thing, well, then I can just go around the circle perfectly, right? But if my orbital equation was much too complicated, like it normally is when you're doing physics, it's not a simple like orbit you can just write a closed form equation for. I have some complicated physics I'm trying to simulate, right? Then what I know is I only get an answer at an instant in time, right? I only can ask at this moment what is like the force on this thing. And so let's imagine for a simple equation like something like this, where we know everything, we know exactly what it should do, just to illustrate. But you have to remember, you can't do this in normal physics. The equations are much too complicated. They cannot be analytically integrable, period. Right? What happens to something like this equation? Well, what we know is that at any point on here, if we were to sample what the force is, well, the force is like something like, or the direction is something like this, and the force is something like this or something, right? So, we know that we're always getting a force that looks like that, and we produce a motion that looks like that. Tangent, right? It's always tangent to the circle, right? But since we're looking at a linearized version at an instant in time, what happens if we actually are taking a time step here? Well, if you think about what happens on the arc, I always get a little further away, right? Because what I'm looking at is I was supposed to trace off, if I look at just a little version there, I was supposed to trace off something that looked like this, right? And I had a motion, a force that looked like this, and a motion, a total motion, when I added my old motion and my new force, a total motion that looked like that. I get a little further away from the circle. And then the next time out, a little further away from the circle, right? I go out, right? And the bigger my time step, the further I go out, right? Because if this time step is huge, I'm way off the circle, right? So those instantaneous linear solutions, they're right for an instant in time, but when you try to take it fixed, a discrete actual time step instead of a continuous integration, it's wrong. And this is where you get into second order, third order, fourth order, fifth order, Runge-Kutta, all these like integrators. They try to correct for this by, if the thing is sort of maybe a parabola or a cubic, then we can get it exact and stay on there. So we get an actual curved update, right? And so on. But fundamentally, you're just fighting the problem. You're always going to be off, right? And so what happens is, in these circumstances, anything that's a forward, so forward Runge-Kutta, forward Euler, any of these sorts of integrators, that update the step, they all do some kind of really bad feedback overshoot, right? So as the time step increases, they fly off the circle, they fly into the circle and out, they do all kinds of crazy stuff, right? And they're all because of that same fundamental problem of, we take a look at the function, we're sampling it, and we're going off the circle, right? The way that backwards ones work is, if you imagine this is really just a field, right? So remember, if I've got equations that I can plug a point in space and get my orbit out, this is how physics works. We have some stuff we feed in, right? Then I could have fed in any point, right? Any point would have told me an answer to that question, right? So when I asked this question, any point would have told me. Does that make sense? So if I was here in my orbit and I ask what the force is, it's going to tell me, the force is like this or something. And it's going to tell me that once I sum those forces together with my previous velocity, I get this, and I'd be out here, right? Well, if I asked for out here, I'd get the same thing. And if I asked for out here, I get the same thing, just adjusted for how far away I am. So the gravity gets a little stronger or a little weaker, and that's, right? So again, backwards integrators, what they do is say, find the point, wherever that is, whose motion line would point back to here, right? And what that's going to do is tell me, like, oh, actually, since if I look, right, at trying to get the right motion line, if I was to ask this point, well, that wouldn't, the answer in the forward case, that wouldn't do it, because the tangent here looks like that. So the inverse tangent looks like that, and I don't get back to where I wanted to be, right? So the answer would be, well, all right, so if I look, it's probably like, I don't know, maybe somewhere like here, right? Gives me that. Maybe somewhere like there gives me that. And so what you see is rather than a thing that adds force to the system in some direction kind of violently, what we actually get is something that removes force from the system. It will take less force now because I will actually undershoot, right? And unlike ones, even these ones that undershoot, they would undershoot kind of badly and go off this direction or out this way. These will always find some place that had less energy in the system than the one before it, right? Than the forward version. And so what you will find is that if a forward version would have spiraled out, this one will spiral gradually inward until it eventually stops orbiting altogether, right? Okay. So that stamp paper, really all that is it saying, let's do this. Let's do something that takes energy out of the system instead of one that gives energy into the system, so that we know that over time, our fluids will always regress back to no movement, eventually. Again, perfect for games. We don't want things to explode, right? We really don't want them to explode. We don't care if they gradually lose energy and reset back to their original form, because we can always add some more energy into the system if we need to. And generally speaking, we want this anyway. Our fluids kind of want to come back to rest, right? So that's fine too. So that's all that paper really was talking about. They also do a Fourier domain transformation to do, there's a long story about some other things they do in that paper, but that's really all it was, right? Is that super relevant to games? Well, yes and no. It's not that important in some sense because really we kind of know this. We know that backwards integrators do this. It was a good contribution because people hadn't thought about backwards in Euler with respect to fluids, and so that was a really good contribution and super important. Is it what you want to do today? Not really. Yes, you probably do want still a backwards solver in a way, but do you want to only do grid-based methods for fluids? Absolutely not. So if you're starting today, you wouldn't start with the stamp stuff. You would start with stuff that's kind of many generations down from that. And typically what people use now is what are called like mixed ways of simulating. The stamp paper just does finite element. So all it does is a grid, right? And it simulates on a grid. That's not a very good way to simulate fluids anymore. Typically what you now do is you have particles and a grid, and you use those two things together to simulate your fluid, if that makes sense, right? And so the stamp paper is good. Understanding it's very good. It was a very good paper at the time. Is it something you want to start with today? No. That's, I guess, the way I would say it. And hopefully, now that you maybe see a little bit what I'm talking about with the backwards roller, you can see what was the important contribution to the paper. It was that. It was how do we get backwards integrators into fluids in an easy way. Right. All right, I'm going to go ahead and shut it down because I need to go have some lunch. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code. So if you want to play around with that lighting and maybe figure out what we should take as our next step, you could do that. I'll be back here tomorrow to do exactly that. I hope to see you back here for that. I think we've got a little bit of a better handle on the reconstruction now, and I'm really happy about that. So I think we know how to push this. I think we know what to push on now. So we'll try some things. We'll see what we can do tomorrow, but I'm excited about that. I think it's going in a good direction. That's it for today. So hope to see you back here tomorrow. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.